Okay, so welcome everyone to the second day of the second week. So today our first speaker is Neil Strickland, and he will continue his talk on ambidexterity. Okay, over to you.
Thank you. Okay, so yeah, we'll continue with talking about ambidexterity. So remember the deal with ambidexterity is we're looking at situations where we've got a functor where the left adjoint and the right adjoint are the same. And if you remember, yeah, so maybe you'll, yeah. So one example we wanted to say, you've got some functor Q from X to Y of finite infinity groupoids. Then we had curly Kx is the set of kind of X parameterized families. Of Kn local spectra. Yeah, Kn was Morava K theory, and we had a category of spectra, had various people talking about that. So we want to look at this continuous families of Kn local spectra parameterized by X. And we've got this Q upper star from Ky, Kx. It's a left adjoint. Left adjoint Q shriek and right adjoint Q star. And then the claim is there exists a natural transformation nu from the left adjoint to the right adjoint. And nu is an equivalence. Say an isomorphism. Okay, and I mentioned earlier that this is done by a kind of recursive procedure. You have these finite infinity groupoids, so all their homotopy groups vanish past some point. The point at which the homotopy groups vanish, that's the kind of truncation level. And in order to sort of prove that to show that this nu exists at level n, you need to already know that nu sort of is an isomorphism at level n minus 1. And so we're going to just have some little bit of a preview of that sort of recursive business here. And it turns out that we talk about I talk about the truncation level, about the level above which the homotopy groups vanish, and that sort of seems to say that you should start with 0 because you've only got pi 0 for a space. But it turns out you can kind of start at level -2. And so we're going to have a bit of a discussion about that to start with. Okay, so we're going to consider some category curly C, which has all finite colimits, or finite limits and finite colimits. And we might, and some functors of groupoids, Q from G to H, but as mentioned previously by this kind of Kahn formula for pointwise calculation of left and right Kahn extensions, anything we might want to say about a general functor Q from G to H can be reformulated in terms of functors C from G to 1. Well, this G might be different from that G. Okay, so we're going to say that G is contractible. Actually, yeah, so there's a slight error here. So G is contractible, it has to be non-empty, and also has this property that there's precisely one morphism from X to Y for any X and Y. And that's equivalent to saying that the unique functor C from G to the terminal category, that's an equivalence of categories. Okay, so in this case, I want to claim that you've got ambidexterity for any category curly C. Right? So why is that? I mean, you just pick say, I didn't say it here, but I should have said it that G is non-empty, so we can choose an object A. And then if you choose an object A, well, C lower star is the inverse limit of the functor. So here, capital C is supposed to be a functor from G to curly C. And I've got too many C's here, really. But, and then C lower star of that is just the inverse limit. And so by definition, universal property of the inverse limit, you've got these maps PA from the inverse limit to CA. And then similarly, you've got a universal property of the colimit. C lower shriek is the colimit of the functor, and there's a kind of universal property of colimits formulated in terms of these morphisms IA from CA into the colimit. And so we compose these, you get a map from the inverse limit to the co-limit. And because it's contractible, it's easy enough to see that this morphism rho here, it doesn't actually depend on my choice of A. And also that this is going to be an isomorphism. Okay, so this is our level -2. If you've got a contractible category, then there's really nothing interesting to say about limits and co-limits indexed by a contractible category, and they're just the same. So, so you always have ambidexterity at this level -2. Yeah. Remember for a general functor Q, the Q lower shriek and Q lower star, we calculate them using these comma categories. Maybe we'll just have a quick reminder of the definitions there. So we've got so you've got a constant functor CB from this, and then any and you've got some functor C from G to category curly C. Then you get this kind of let's call it C tilde as a map from as a functor from Q. Okay, so just by composing with the projection, then you get this functor C tilde, and then so Q lower shriek C evaluated at B is just the okay, so we've got these Kahn formulae for the Q lower shriek and Q lower star. So in order to understand whether this is the same as this, we just need to know whether CB lower shriek is the same as CB lower star. And so yeah, we can reduce everything to this kind of this first case here. And so yeah, so when is this? So but to interpret that here, yeah, we need to know when are these comma categories, when are they contractible? And it's a little exercise that the comma categories here are contractible if and only if Q is an equivalence. So if Q is an equivalence, then Q lower shriek and Q lower star are the same. Okay, so that was a case where G is contractible. G is contractible is called what's level -2. Level -1 is where G is either contractible or empty. So we've already dealt with the contractible case, but what about if G is empty? Okay, so so G is empty, then there's a unique functor from the empty category to anything. So this C lower G, the functors from G to C, that's just that. This is just a terminal object. It's got a terminal category. Only got one object, and you apply C lower shriek to it, you get the initial object of C. You apply C lower star to it, you get the terminal object of C. And there's always there's a unique morphism from the initial object to anything, or a unique morphism from anything to the terminal object. So we certainly get a unique map nu from C lower shriek to C lower star. And when is that an isomorphism? It's an isomorphism if and only if your category C is pointed. This is actually just the definition of pointed, really. Category is pointed if there's an object which is both initial and term. So like category of finite-based sets is pointed, or finite-based topological spaces pointed. Category of abelian groups, of course, is pointed, or category of all groups is pointed. Yeah, the trivial group is both initial and term. Okay, so this is level -1. So yeah, so ambidexterity works at level -2 for any category C whatsoever. Ambidexterity works at level -1 only for pointed categories. Okay, and so this is what we get for this case where you just got G to 1. What about for an arbitrary Q like this? So we need to ask ourselves, when is it true that all the comma categories are either empty or contractible. And that's the case if and only if Q is a full and faithful embedding. So in the case of a full and faithful embedding and a pointed category C, then for any, then we have this ambidexterity isomorphism, Q lower shriek is Q lower star. So yeah, ambidexterity works at level -2 for any category, at level -1 for pointed categories. Okay, what about level 0? So level 0 is kind of where G is a finite set, or is an equivalent to a finite set. So remember, set we can regard as a groupoid just by saying that the only morphisms are identity morphisms. So and those are the kind of groupoids which we count as level 0. And in that case, we can so what's CG in that case? The functors, in this case, the functors from G to C is just the product of copies of C, one for each element in the set. And so we want to get so we want to define a new from the co-limit to the limit. Okay, so that's the same as a functor, a natural map from the co-product of copies of some family of objects CX to the corresponding product. Okay, so now if we want to get a map from this co-product to that product, then that means we have to give maps from, because just using the universal product of the product, universal properties of the co-product and product, to give a map like this, we need to give a map from CX to CY for every X and Y. So how are we going to do that? Well, if X is equal to Y, then we just take the identity. X is not equal to Y, well, how can we possibly produce a map from CX to CY? Kind of completely independent objects, apparently. Well, but we're assuming that C is pointed, so we can just take the 0 map. Right? A pointed category, then you've got a kind of unique morphism that goes from any object to the 0 object, because the 0 object is terminal, and then from the 0 object to any other object, because the 0 object is initial. So we get these 0 maps from CX to CY in this pointed case, and this gives us a map here from the co-product to the product. And so when is that going to be an isomorphism? Well, that's precisely the definition, what it means for C to be a semi-additive category. Semi-additive category is where, a pointed category where the maps from the co-product to the product, finite co-product, finite product are isomorphisms. So that's what we call level 0, when you've got finite set here. And so you have ambidexterity at level 0, if and only if your category, for this case here, where it's just G to 1, you get ambidexterity if and only if G is a finite set, and you've got semi-additive category. And what does it mean for all the comma categories to be finite sets or equivalent to finite sets? That's going to happen if and only if Q is actually a faithful function. So again, that's a little exercise. So we've got semi-additive category, faithful functor, then we've got left and right adjoints of the same. Okay, so suppose we've got, in this case that we mentioned, semi-additive category, ambidexterity at level 0. And so the kind of point about a semi-additive category is that the Hom sets have a natural structure as abelian monoids. Most often abelian groups, but in general just abelian monoids. Okay. So that means you've got some family of morphisms, Fi from C to C prime, then we can consider their sum. Okay. So now we're just going to explain a different way to think about what this sum is, which kind of makes the role of this ambidexterity thing a bit more obvious. Okay. So how do we define the sum of these Fi's? Well, we can take, we've just got one object C, but you can take the I-fold product of it. Product of I copies of the same C here, and you have the product of the F's here, and you've got or similarly, you can take the direct sum of I many copies of C, and you've got the direct sum of the maps going down there. And then you've always got a diagonal map from C into the product. That's kind of formal, and similarly, you have a co-diagonal map from the co-product to the product, right? Right? This is given by the universal property of the coproduct. This is given by the universal property of the product. And so we've got these maps here and here, and then then we've got these maps nu. So the existence of nu comes from the fact that the category is pointed, and the fact that nu is an isomorphism here, that comes from the fact that it's a semi-additive category. And now the sum of the maps is what we get by going, you take this diagonal, and then you go either way around this triangle, this square here, but using the inverse of nu, and then you take the fold map, and then this composite from C to C prime, that's the sum of these maps Fi. And so this is a way of describing the sum, which kind of makes it clear what the role of the ambidexterity isomorphism is. And we could write this in just basically just the same thing, slightly different notation. And what's this product of copies of C here, right? So firstly, we take our single object C, and then you want to consider the family of objects, which is just, each object in the family is C again. So that's what to convert this single object C into an I-indexed family, we do C upper star. And then to take the product of the element of the objects in that family, we apply C lower star. So this product of copies of the same object C is C lower star, C upper star. And similarly here, whereas here you take a single object C, you form the corresponding family by applying C upper star, and then you take the sum of that family by applying C lower shriek. So this is C lower shriek, C upper star here. And then this diagonal map here we can think of as being the unit of the C lower star, C upper star adjunction. And then this co-diagonal map here we can think of as being the co-unit of the other adjunction. Okay. So this is how we get our map. This is how we take the sum of some parallel morphisms. Yeah, okay. So now suppose you've got a finite groupoid, G, and you've got some C and CG, where again, C is semi-additive. We want to kind of go to the next level and think about whether we've got ambidexterity at level 1, whatever level 1 is. We've not actually been very precise about what level 1 is going to be yet, but anyway, we're going to need to define this nu first. And so and we do the same thing that we actually did when considering kind of representation theory. You want to get a map from the co-limit to the limit, so we need to get a compatible family of maps from Cx to Cy for all possible x and y. And so whenever you've got a U, a morphism U from x to y, it induces a map U lower star from Cx to Cy, and we want to take the sum of all those possibilities. That's the way we get a map. Yeah, and then this is kind of, because we've taken the sum of all possibilities, this is kind of consistent when we change x and consistent when we change y. So this will induce a map from the co-limit to the limit. But yeah, so we need to form this sum, and to form this sum, we're doing this business we did up here using the ambidexterity at the previous level. So that's kind of a preview of the way we're going to do this sort of recursive thing. Okay, so now we're going to change gear a bit and start talking about infinity categories. So yeah, we could. So all this stuff we're doing about ambidexterity, in principle, we could do it with using model categories or some other kind of topological categories, some other kind of foundation. But in practice, most of the kind of current literature is written in the language of infinity categories. So we're going to have a little bit of a preview of that. But we're not going to give any details, just a kind of general flavor. So like I say, there's purpose of infinity categories is kind of, well, it's to sort of take the place of stuff that people used to do using ordinary categories or topological categories or model categories. Part of the story is, obviously you want to do kind of limits and co-limits, but when you're doing kind of homotopy theory type things, you don't really want actual limits and co-limits. You want homotopy limits and homotopy co-limits. And part of the main purpose of infinity categories is to set up a framework in which kind of the theory of homotopy limits and homotopy co-limits kind of works in a very, very similar and parallel way to the way that limits and co-limits work in ordinary categories. So a kind of basic example, let's think of a space, and we're going to try and produce a category from it. And sort of our first attempt, we're going to look at this Px from A to B. That's just a set of paths, space of paths, Px, A, B. So it's set of those continuous maps from the unit interval to X, which sends 0 to A and 1 to B. Okay, and then we have a composition rule. Okay, the usual sort of thing. You've got some path from B to C, path from A to B, and you define a composite path from A to C. You do U at double speed in the first half second, and then you do V at double speed in the second half second. And unfortunately, this doesn't give us a category because composition is not strictly associative. Very well-known thing from the definition of fundamental group and so on. So we can fix that just by passing the homotopy. We just take, instead of looking at this space PXAB, we take pi 0 of it, the set of path components, or it's a set of pinned homotopy classes of paths. Pinned homotopy, I mean that the homotopy that doesn't move the endpoints. So we can do this. This gives us a groupoid, a path that is a category, because U composed with V composed with W, you do it one way or the other way. Those paths are not actually the same, but they are pinned homotopic to each other. So we've got a well-defined composition, well-defined and associative composition law on this pi X category. It turns out, of course, you've got a path from A to B. You can just reverse it to get a path from B to A. And that turns out to be an inverse morphism in this pi X category, so it's a groupoid. But if we just pass immediately to homotopy, we lose too much information. That's not what we want to do. Well, let's think about what would happen if we had a map from the full n simplex into X. Let's maybe draw a picture for n equals 2. So we've got some U, say, from delta 2 to X. So here's my simplex delta 2. So you've got an E0 here and E1 here and E2 here. So you've got A0, say, is U of E0. So these are points of X. Now, so U applied to the edge from E0 to E1 gives the path. Let's call it U01. And so you get U12 in PX from A1 to A2. And U02 is in PX A0, A2, and okay, so you're supposed to think about it this way, right? I mean, you've got a path from, you've got a kind of broken path from E0 to E1 to E2, and then you've got a single path from E0 directly to E2, and then this kind of stuff that's happening in the middle, where you can use that to push the broken path over to the single path. So you can think of that as kind of being evidence that that U02 should be thought of as a possible composite, right? There isn't kind of like a single well-defined composite, but there's a bunch of different possible composites, and this U is evidence that U02 should be thought of as one of them. And then you can do that for a general n simplex. You get n plus 1 points and a bunch of paths and some extra information which kind of witnesses the fact that Uik should be is a choice of Ujk composed of Ui. So we look at all these sets. Pxn is the set of all continuous maps from delta n to X, these form what's called a simplicial set, and it's a simplicial set with particular properties, infinity category is defined to be a simplicial set with those properties, and infinity groupoid is defined to be a simplicial set with some extra properties, and then it works out that this Px is going to be an infinity groupoid, and this kind of construction is supposed to give you an equivalence in some appropriate sense between the theory of topological spaces, the homotopy theory of topological spaces, and the theory of infinity groupoids. Okay. But I said, you know, infinity categories are supposed to be some kind of generalization of categories. So let's see how that kind of fits together. Okay, suppose we've got an ordinary category. What we mean by an n simplex of C, I mean a family of objects, Ci from I from 0 to n, and with morphisms Uij from Ci to Cj, which compose in the obvious way. So Uik is the composite of Ujk and Uij. So that's what I mean by an n simplex. And so NCN is the set of all those n simplices. And so that's kind of a bit of a similar sort of thing as the Px that we had on the previous slide. And it's a simplicial set and it has the right properties, it turns out, for it to count as an infinity category. Yeah, in practice, you know, the way that people speak about these things, you know, we don't really distinguish between NC and C. When we want to talk about NC, we just sort of say C considered as an infinity category, something like that. Okay, so that's what, but that's, yeah, so that's what we do with kind of ordinary categories, but the kind of purpose of infinity category theory is basically to deal with kind of stuff, homotopical stuff. So we need to have something like topological categories or model categories or something. So one way we can pass from a topological category to an infinity category is by the so-called coherent nerve. Okay, so we've got a topological category C, so that means that each of these morphism spaces, sets CAB, that's actually a topological space. And so now we're going to define what we mean by an n simplex of C. So it's kind of again, it's going to be a system of objects Ci, just the same as we had before, from I0 to n. And then you're instead of just having a single, so here we had a single morphism from Ci to Cj, but now I'm going to have not a single morphism, but a continuous map, a whole cube's worth of morphisms indexed by the cube of dimension j minus I minus 1. Yeah, so this is okay. So how am I supposed to think about this? Well, yeah. So in particular, in this cube, you've kind of got the top right corner where all the coordinates are equal to 1, and so you apply Hij to this this 1, 1, 1 thing, and then that gives you an element of this set. In other words, a morphism Uij from Ci to Cj. And then if you think about how these Hijs work, well, in particular, they give us some homotopies, which witness the fact that Uik is, you know, it's not actually equal anymore. I mean, up here, Uik was equal to Ujk composed with Uij. Here, we've just got like a homotopy, a path in the morphism space from this to this. And, you know, and then, you know, but you've got more than that. I mean, you've got all this whole Hij, a whole cube's worth of stuff. And there's a bunch of combinatorics that you have to go into to understand how it all fits together. But basically, these are providing these homotopies and then further higher homotopies to show that all the lower homotopies are compatible with each other. And so again, we've got this kind of set of n simplices of C, and they give you a simplicial set with the right properties to be an infinity category. And notice, of course, I mean, here this is a topological category, CAB is a space, but I mean, ordinary category, we can just regard it as a topological category. CAB has the discrete topology. But if CAB has a discrete topology, then this continuous map like this has to be constant. Okay, and so because of that, you know, you see that this this first definition is really a special case of the second. And so we could do this just with the category of spaces or with the category of orthogonal spectra. And those are both topological categories. They would give us infinity categories. In fact, however, if we just do this in the most obvious way, we don't really get the right answer. You get kind of the strong homotopy category of orthogonal spectra, where you haven't actually inverted the weak equivalences in the right way. So, and I'm not going to go into more detail about this, but there's a similar constructions in the same spirit where but where you start with a equivalent model category or some other category in which you've got a notion of weak equivalences, and you kind of modify this definition of the coherent nerve in a certain way in order to invert those weak equivalences. So a few more things about infinity categories. So in particular, it's a simplicial set. So you've got infinity category is a simplicial set. So it's got set Cn for every natural number n. So C0, you can think of elements of C0. You just think of as objects of the infinity category. C1, you think of as a set of morphisms, and every morphism has a source and a target. So you get the collection of morphisms from A to B for any pair of objects A and B. And you don't, like in the path category example, there isn't a kind of well-defined composite. There's given a pair of apparently composable morphisms, there's not a unique composite, but there's a family of potential composites which are indexed by a certain subset of C2. And in fact, in the first instance, you kind of think of this as being a set, but there's a way to kind of enrich it and think about there being a kind of actually a space of potential composites. And this is the way that most of these things happen in infinity category theory. A bunch of places where you would normally expect to find a set. The theory of infinity categories provides you with a space, and in a bunch of places where in ordinary category theory there's a kind of unique element with some property. In infinity category theory there'll probably be a contractible space of things with that property. But it's kind of central to the philosophy that having a contractible set of choices is basically as good as having a unique choice. And similarly, you've got the CAB0. I said this is a set of morphisms from A to B, and in the same way, there's a kind of slightly more elaborate procedure where we kind of think of this as this CAB0 as being not just a set, but it's the set of vertices of a simplicial set or a space CAB. And that's kind of how things generally work out. Anytime you're dealing with infinity categories and you have a kind of set of things with a particular property, then usually you can sort of enrich that somehow so that that initial set is actually the set of vertices of a naturally defined simplicial set or space. Whenever you've got a infinity category C, then you can make a homotopy category. So again, so the object of the homotopy category is just your C0. And your morphisms of the homotopy category, that's some appropriate quotient of the C1. And you can set things up with a construction of infinity categories from topological categories or model categories in such a way that you get the same kind of homotopy category as you did in previous formulation. Yeah, and then what's a functor of infinity categories? Well, it should obviously, as you'd expect, you have to have a map F0, which sends objects of C to objects of D. You have to have a map F1, which sends morphisms of C to morphisms of D, which is kind of compatible with source and targets. And then you'd kind of want to say that functor should preserve composition. But there is no well-defined composition in an infinity category, so we have to kind of try and formulate that slightly different way. But as I said, the kind of potential composites are sort of indexed by C2. So if we've got a map F from F2 from C2 to D2, then that's somehow encoding compatibility of F with composition. And you shouldn't stop at 2. To make everything fit together properly, you have to have maps Fn from Cn to Dn for all n, and they have to be simplicity compatible. So a functor of infinity categories consists of maps Fn from Cn to Dn which are compatible with their relevant structure. And a kind of key point about how all this fits together. If you've got a space X, or as you said, space X we can consider as an infinity category or even as an infinity groupoid, and some other kind of topological category C. Well, you've got a topological category C, then it's kind of very natural to kind of think about continuously parameterized families of objects of X, parameterized by your space X. And there's kind of various ways you can do that in the more traditional theory of topological categories. But from the kind of Lurie point of view, the right notion of a parameterized family is just a functor, right? So X can be regarded as an infinity category by taking this kind of path category construction, and C is an infinity category, and you look at functors in this sense from X to C, and those are that's the correct notion of a local system of C objects parameterized by X. Let's have a few words about colimits and limits in infinity categories. So ordinary category C, what's kind of the most basic degenerate example of a limit is the terminal object. And so terminal object T is terminal if and only if there's precisely one morphism from A to T for every A. In other words, the set CAT has size 1. Infinity category, the CAT, well, we can make it as a version of the CAT which is a space, and we want to say that T is terminal if CAT is not just a single point but is contractible for every A. So as I said, in infinity category theory, contractible space is kind of the right notion to generalize what normally be a point. And then dually, an initial object CIB should be contractible. Then, and then in ordinary category theory, all limits can be thought of as terminal objects in an appropriate auxiliary category. You've got a diagram U from some indexing category I to C, so functor U from I to C. Then there's this category of cones. Maybe you have a reminder of that. So cone on U is a pair kind of A. So A is in C, and F is a family of morphisms. Okay, so there's this category of cones. So a cone is an object of C together with a family of morphisms from each A to each of the UIs that's compatible in the usual way with the morphisms in I. And then a limit is essentially by definition just a terminal object in the category of cones. And so so we want to do this in the infinity category as well. There's a little bit of work to do to understand how we should translate this definition of the category of cones into infinity category theory, but that can be done. So you can define an infinity category of cones, and then we know what we mean by a terminal object in an infinity category, and that's how we define the notion of a limit in this world. So we need to kind of pay a little bit of attention to sort of what's the kind of how this interacts with forming homotopy categories. So yeah, you want to look at morphisms from A into this inverse limit. Okay? So we could think about morphisms in C, but more often we're kind of mostly working in the homotopy category. So we want to think about morphisms in the homotopy category from A into the inverse limit, and that's just that's just the same thing as morphisms in the homotopy category associated to this functor category from the constant diagram to B. Okay? So this is kind of an obvious sort of analog of what happens in ordinary category theory. but the kind of point to worry about is just there's kind of two different things you might think of putting here. Firstly, you can just take the diagram category, the category of functors from I to C, and take the homotopy category associated to that. Or you could consider the category of functors from the homotopy category of I to the homotopy category of C. And there's a functor from this guy to this guy, but it's not necessarily an equivalence. Okay? And so this is the kind of point that might cause confusion and difficulty. But as long as we remember to work in the right categories, then this is how we kind of basically work with inverse limits. And so that was inverse limits. Of course, you do co-limits just by working the opposite category. And most of the time, existence of limits and co-limits is not really an issue. So most of the kind of categories that most of the ordinary categories that people normally work with, there's some kind of very formal way to construct limits and co-limits. It's harder work to set up the relevant theory in the infinity world, but Lurie's done it for us. So most of the time, we don't have to worry about that. And there's also definition of adjoint functors, which is kind of maybe a bit more subtle than you might immediately think. But there is a definition of adjunctions, which we won't really get into. But I'll just mention that if you've got an adjunction in the junction like this of infinity categories, then it does give you an adjunction of the homotopy categories, which is mostly what we want to deal with. Okay, so so we just have a little bit of a review of spectra, orthogonal spectra. So I'll start just by recording notation for spaces. And so curly T is going to be the category of spaces, and as is usual in algebraic topology, we're going to work with compactly generated weak Hausdorff spaces. Just a technical condition to make sure that the mapping spaces work in the correct way. T star is the category of base spaces, base point generically called 0, but sometimes called infinity. We take the wedge product of spaces X and Y. Well, you take a disjoint union of X and Y, but you kind of glue together the base point in X with the base point in Y. Real deal. So X is like this with a base point here, Y like this with a base point there, and then X wedge Y. Let's connect them together at the base point. And then X smash Y, take the product X cross Y, and then you collapse out the axes. So here, X is like this with a base point there, and Y like this with a base point here. X cross Y is like a square like this, but everything on the squiggly line gets collapsed down to a point, because this is kind of 0 cross Y. That's X cross 0. And so when you collapse that down, you kind of get a lens here. Okay. And then fxy is the space of base maps from X to Y with a suitable topology. It satisfies these kind of adjunctions here that maps from X to fyz, that's equivalent to maps from X smash Y to Z, and maps from the wedge product X wedge Y to Z, that's product fxz cross fyz. And some places we're going to need to assume that X is a CW complex or has the homotopy type of a CW complex, or to make other kind of adjustments like that, but I'm not going to be careful about any of those things. And then by this kind of coherent nerve construction, or sort of slightly modified to invert the weak equivalences, then we regard these things as being infinity categories. Then in order to form spectra, we need to say something about finite dimensional real inner product spaces. The category curly L, that's finite dimensional vector spaces over the reals equipped with an inner product. So any object in here is kind of just isomorphic to Rn with the standard inner product. So you could just formulate this in terms of the standard Rns, but for many purposes, it's kind of more natural and more elegant to allow any vector space with an inner product. So in particular, by doing it this way, we can sort of consider arbitrary subspaces of Rn with their induced inner product, and they're still objects in this category. Okay, so then if any such thing, we have a sphere. You take the one-point compactification, V union infinity, and we take infinity as the base point, so that's our sphere S to the V. So V is dimension n, then S to the V is homeomorphic to the standard n sphere. And the way the smash products work, S to the V smashed with S to the W is the same thing as S to the V plus W. So I'm going to define an orthogonal spectrum this way. So you could define it just in terms of the Rn's, but I'm going to define it in terms of arbitrary inner product, finite dimensional inner product spaces. You get equivalent category, but this formulation is something more natural for some purposes. So it's continuous functor from this category L here to base spaces, but equipped with these suspension maps from S to the V smashed with XW to X V plus W, subject to various axioms that you can imagine. Let's do it again. So, obvious kind of compatibility if you try and do this sort of suspension thing twice, for example. And so curly S is going to be our category of spectra, or I'm just going to say these are, or you might call these orthogonal spectra, but I'm just going to call them spectra. And so they form a topological category, and you convert that to an infinity category in the usual sort of way. Actually, we're going to have to. The usual sort of way has to invert the weak equivalences, so we need to explain what the weak equivalences are. So we need to define the homotopy groups of a orthogonal spectrum. So for n greater than or equal to 0, I'm going to take, you've got the maps from the V sphere to XV and smash with S to the n here. Take homotopy class of maps here, and you take the colimit over V. It's kind of a little, it's kind of more common to sort of just define the colimit over the sequence of standard inclusions of Rn into Rn plus 1. It's actually a little exercise, but it doesn't make a difference if I take the colimit over the whole category curly L. And that's actually, that formulation actually makes things work more nicely if we want to do the equivariant version on various other purposes. So that's what we do for the non-negative homotopy groups. And if you want negative homotopy groups, pi minus nx, then instead of having an s to the n on the left, you put in a shift by r to the n on the right. So we're going to say that a map is a weak equivalence if and only if these pi star f is an isomorphism. And so when the right way to form the corresponding infinity category, we're going to adjust the details in such a way that we invert the weak equivalences. So what are basic examples of orthogonal spectra? There's a suspension spectrum, so sigma infinity t for a space t, so the value of that at a vector space v, you just take s to the v smashed with t. And so we won't really just, the sigma infinity functor, before we pass to homotopy, sigma infinity just gives us a full and faithful embedding of spaces in orthogonal spectra, so we won't really distinguish too carefully between t and sigma infinity t. Another one that we can just write down in a nice way, you just take your vector space V, you just take the free abelian group generated by it. And so that's it's really not very obvious what's the right topology to put on that set, but I'm not going to go into that. But there is a natural topology to put on this HV. with respect to which all these the action of L is continuous, and then these suspension maps. There's a kind of fairly natural kind of straightforward way to do a suspension map from S to the V smash HW to HV plus W. And if you set up the topology right, that'll be continuous. And so this is give us an orthogonal spectrum, and it's going to work out that pi 0 of this one is Z, and all the other homotopy groups are trivial. So this is what's called the Eilenberg-MacLane spectrum. It's a nice model of it. Another one, we're not going to really use this, but it's a nice example to write down to see how the kind of theory of orthogonal spaces, orthogonal spectra works. So I want to define MO of V. So that's the set of pairs little u comma big U. So big U is going to be a subspace of V plus V, and it's going to have the same dimension as V. So it's a kind of middle dimensional subspace of U plus V. Little u is going to be an element of big U. Okay? So this thing in this first curly brackets here, this is a locally compact Hausdorff space, a manifold even, and then I'm going to just take the one-point compactification. So this is MOV, and then so a whole bunch of extra work you need to do to kind of understand anything useful about the properties of MO, but I mean, here is the kind of key property that comes out of thinking through the geometry of this. Pi n of this spectrum MO, that's the set of cobordism classes of closed, smooth, n-dimensional manifolds. So this gives us a kind of nice connection between stable homotopy theory and differential geometry. Then we need to understand some stuff about smash products of spectra. So oh, this is a typo here. This should be. Before we say that, I mean, how do we define the tensor product of abelian groups? So M tensor n, what is that? That is basically defined by the property that Hom M tensor n T I mean, the point about the tensor product is that homomorphism M tensor n to T biject with bilinear maps from M cross N to T. And so, you want, and the sort of smash product of spectra is kind of like a tensor product, and it represents kind of the analog of bilinear maps in the appropriate way. So we have to say what do we mean by bilinear map? And so, unfortunately, there's a typo here, but pairing from X and Y to Z consists of maps from X, U, right here. Supposed to have maps from X, U, smash Y, V, to Z, U plus V. Okay, that's what we mean by a pairing from X and Y. They're supposed to have various kind of compatibilities with the structure maps for X, Y, and Z. And yeah, so then there's this the smash product X slash Y, and it's defined in such a way that pairings like this, which you should think of as being like bilinear maps from X and Y to Z, they just biject with morphisms of spectra from X smash Y to Z. Basic calculation is that, well, you just do this with suspension spectra. Remember, any base space T, we have a suspension spectrum sigma infinity T, and the sigma infinity functor respects smash product. So here we've got the smash product of spectra. There we've got the smash product of spaces that we defined before, and they're kind of compatible via sigma infinity. Similarly, for both the Eilenberg-MacLane spectrum H that we had on the previous slide and the MO spectrum, it's pretty easy to define a map from HU smash H. Well, it's easy to define pairings, HU smash HV to HU plus V, MOU smash MOV to MOU plus V. You can take as an exercise to sort of guess what those are. There's basically only one possible thing you could write down. So these give you maps from H smash H to H and MO smash MO to MO. And these make H and MO into commutative ring spectra. A ring is a abelian group with a map from R tensor R to R, and here the analogous thing in spectra. Another kind of important thing about the category of spectra is that we've got negative dimensional spheres as well as positive dimensional ones. So let's explain that. So we've got A. So here, capital A is going to be an element of our category curly L. So A is a finite dimensional inner product space. And so S to the A is a space, but S to the minus A is going to be an orthogonal spectrum. So I have to tell you, so to define an orthogonal spectrum S to the minus A, I have to tell you its value on another inner product space V. And that's the set of pairs. Well, again, it's a one-point compactification of a certain manifold. And what is the manifold? It's a space of pairs where F is a inner product preserving map from A into V, and then little v is an element. You take this vector space capital V here, and then F is a inner product preserving map, so it's injective from A into V, and then you take the orthogonal complement, all the vectors in capital V that are orthogonal to the image of F. So space of pairs FV like that, that's a manifold, and you take the one-point compactification. You can check that this gives you an orthogonal spectrum, and it represents an obvious functor. I mean, you can check that morphisms of orthogonal spectra from S to the minus A to X, that they just biject with the eighth space XA. And also, this is nicely compatible with the smash product. S to the minus A smashed with S to the minus B is S to the minus A plus B. And so we can use these actually to define a kind of internal Hom thing. And so, another typo here. This should be an A here. Write that down. Okay, so now I started with two spectra here, and then this I've got a functor for every v here, so this actually gives me a spectrum fxy, and it has it's a kind of internal Hom object in the sense that maps morphisms of spectra from W to fxy, they biject with morphisms from W smash x to 1. Okay, so you might think, I mean, so by analogy with, we had S to the A smashed with S to the B is S to the A plus B, and S to the minus A smashed with S to the minus B is S to the minus A plus B. And so you might hope that S to the A smashed with S to the minus A is isomorphic to S0. That's not quite right. There is a natural map from S to the A smash S to the minus A to S0. Kind of easy to write this map down. It's not an isomorphism, but it is a weak equivalence. So in the homotopy category, we can say that S to the minus A smash S to the plus A smash with S to the minus A is just S0. And then we also, there's these kind of constructions of the wedge and the smash product, well, the wedge product and the Cartesian product. These we can just do level-wise, right? So x wedge y at v is xv wedge yv, x smash y at v is xv across yv. But there's a warning here. Incidentally, there's a the spaces so x smash y is defined as a just as a quotient of x cross y. And for spectra, there is no natural map. These are kind of spectra. These are sort of independent things. But on the other hand, there's a map. There's a map from x wedge y to x cross y, and this is a weak equivalence. Okay, this is saying that the category is semi-additive, and the co-product to map from the co-product to the product to a weak equivalent. So, and yeah, you've kind of seen previously the fact that the category of the homotopy category of spectra is semi-additive, you know, all the, or even additive. Morphisms, the morphism sets in the category of spectra are abelian groups. And that's kind of reflected by the fact that this here is a weak equivalence. Yeah, sure. Various different orders in which you could do things. I mean, you can prove at least, well, you can prove in reasonable generality that this is a weak equivalence kind of rather directly without, and then deduce the semi-additive structure, or you could do the semi-additive structure first and then deduce that this is a weak equivalence. But yeah, so actually we'll say a little bit more about the semi-additive thinking. Okay, so two ways that we can do a suspension. And so one way to do the suspension, which I'm going to call sigma, is you just take the suspension of individual spaces. So the suspension of a space, just smashing with a circle. So we could just do that. Or we could do this other kind of suspension, the shifting thing. So the sigma prime x evaluated at v is just x at r plus v. And so just it's kind of built into the definition of orthogonal spectra. Remember that you get a map from S1 smash xv to xr plus v. That's kind of part of the structure of an orthogonal spectrum. So you get a natural map from sigma to sigma prime. And if you just look at how remember the homotopy groups are defined as a certain colimit, and you just think about how that colimit interacts with these constructions here, you'll see that the pi n of sigma x is the same as pi n of sigma prime x. So this is a weak equivalence. And you can also do the sort of adjoint thing. You can take omega x at v. So you just this is just pointed maps from the circle to xv. So this is easily seen to be right adjoint to the sigma, and so you've got this unit and co-unit maps from x to omega sigma x and sigma omega x to x. And and by kind of some kind of rather formal argument comparing sigma and sigma prime and omega, how they all fit together, it's quite reasonably formal that this eta and epsilon are both weak equivalents. So if we look at the level of homotopy categories, then sigma is equivalence and the inverse is omega. Yeah, and omega 2 of any y is always a abelian group up to homotopy in a natural way. Remember the standard construction of this, you've got a pinch map from the two-sphere to the wedge of two copies of the two-sphere. Just take S2 and you collapse the equator, and then you just got the upper hemisphere and the lower hemisphere just become copies of it, S2 joined together at a single point. So you've got this map delta from S2 to S2 wedge S2, and so now this gives you a map delta star from the F S2 wedge S2y to F S2y. F S2y is the double loop space, and F S2 wedge S2y is the product of two copies of double loop space. So you've got this map now from loop 2y across loop 2y to loop 2y, making loop 2y, so giving you a binary operation on loop 2y, which is associative and commutative and unital up to homotopy. So loop 2y is an abelian group object in the homotopy category. But we could take y to be sigma squared x for any x, and then omega 2 sigma 2 x is just the same as x by what we set up here. So you get an abelian group, natural abelian group structure on any x. And using that, well, you've got morphism homotopy category from W to X using the group structure on X. You get a abelian group structure on this set, and this makes HS into an additive category. So, question? Remember, so for additive categories, you've got ambidexterity at level 0. You've got a weak equivalence, so you get an isomorphism from the co-product to the product, as we said here. Now I'm kind of being a little bit sloppy about the relationship between ambidexterity sort of in the homotopy category and ambidexterity at the infinity category level. I'm not going to try to be more precise about that. And so, this thing, we can think of it as being the wedge or as being a product, or we can think of it as because we're in a sort of additive context now, it's reasonable to write this as the direct sum. Okay, so there's our additive structure. And I want to, I'm going to want to relate this kind of business about addition of morphisms to this construction that's traditionally called the transfer. So let me explain a little bit about the transfer. So suppose I've got a map F of finite sets. I can apply I can add a disjoint base point to get a map from X plus. X plus means X with a disjoint base point added. And then I apply sigma infinity to that. So I get sigma infinity F plus from the suspension spectrum here to here. And notice, it's easy to see that this is just the wedge wedge of some copies of S naught indexed by X, right? So if I've got X is say A, B, C, then X plus. Okay, so I take a wedge of 0A, 0B, 0C. When you take a wedge, remember, you just kind of glue together the base points. So this is just the same as this. And S naught is just 2 points. So X plus is just a wedge of 3 copies of S. Now HS is additive, so I could also define a map kind of the opposite way. Essentially, what I'm doing is, the image of a point Y here is just the sum of the pre-images. So I could say this, but it's kind of useful. You could say it this way, but it's useful to have a kind of more precise, more geometric model of this, which will connect with the kind of traditional formulation in terms of transfer. So I'm going to do it this way. So so V is going to be the free vector space freely generated by the set X, and so your set X gives you a basis, and I is just the inclusion of the basis in V. And remember, S to the V is just V union infinity, so you think of V as sitting inside S to the V. Now, if I have an open ball of radius halves around the origin in V, it's pretty standard that open ball is homeomorphic to V itself. If you want, here's a formula for it. S of V is V divided by the square root twice 1 plus norm of V squared. This gives you a homeomorphism from V to this open ball. So I can define a map F tilde from V cross X to V cross Y. F tilde of Vx, well, I'm basically going to do, so it's going to cover F, so sort of as my second factor, I just send X to F of X, but I'm also going to send V to S of V plus Ix, and because these have because the S, S gives me a ball of radius 1 over root 2, and these I of X's, these are kind of independent orthogonal basis elements, so the ball of radius 1 over root 2 around Ix is different, is disjoint from ball around I of X prime when X prime is different from X. So you can see that this map F tilde here is actually injective. So an open embedding from V cross X to V cross Y, which covers F in the obvious sense. So now I can define this kind of collapse map going backwards. So I'm going to take this space V cross Y here and add a disjoint base point. Take this V cross X, take this V cross X here and add a disjoint base point. I'm going to define my map C going backwards. C is more or less the inverse to F tilde. Okay, so if I've got a point here that's of the form F tilde Vx, then I just send it back to Vx. That only defines C on the image of this embedding F tilde. But outside the image, I just send everything to infinity. That's called a Pontryagin tone collapse. Well, no, it only depends on X. Yeah, it's the same V. Yeah, so so on the image of F tilde, we just have the inverse of F tilde, and away from the image of F tilde, we just send everything to infinity. And it's again, it's kind of exercise in point set topology to see that this C is continuous. And we've done this kind of point about going through the details of this construction is that by working in the framework of orthogonal spectra, we managed to do this in a kind of completely natural and canonical way. We didn't have to make any choices. Therefore, it's kind of automatically compatible with any group actions that might be around. Okay, but now, so we've got a map here from S to the V smash Y plus to S to the V smash X plus. But now we can smash with the negative sphere S to the minus V, or apply sigma infinity and smash with S to the minus V. We're working, so in the homotopy category, S to the minus V smash S to the V is the zero sphere. So we get a morphism in the homotopy category from sigma infinity Y plus back to sigma infinity H plus. This is an example of what we call a transfer. In particular, you could do this where F is just the map from the 2-point set to the 1-point set. And then your C is just the kind of usual pinch map from S2 to S2 wedge S2. And so the next lecture will kind of explain how this feeds into doing some equivariant stable homotopy theory, which we're going to need in order to do some equivariant ambidexterity things. But I'll stop there for today.
Okay, so are there any questions? If not, let's thank the speaker again.